Okay, let's continue with scale issues in urban remote sensing. I want to start this video with another, say, terminology or term. It's called MAUP. The full name is Modifiable Aerial Unit Problem. So it is a statistical biasing effect when samples in a given area are used to represent information such as density in a given area. Actually, this issue here, this problem here, MAUP, is not exclusive to remote sensing or even to GIS. It's widely distributed in different disciplines when you're trying to sample something within a space. For example, landscape ecology, okay, it's not GIS, but what they care is the spatial configuration and the composition of land covers within space, and how this configuration, spatial configuration and composition impact the environment, impact ecology. So MAUP, since when we're talking about remote sensing, it's naturally having a spatial context. When we're trying to sample something using remote sensing technology, for example, we want to sample some pixels from an imagery to address a specific problem, there is MAUP, okay? And MAUP is more complex than this simple one sentence definition, okay? It is actually twofold, okay? Firstly, MAUP can appear when you zoom in and zoom out. In other words, when the scale changes, your result, your conclusion from the observation could change. That is the first part of MAUP. For example, here, we have a square here. Within this square, we have black dots, okay? So looking at this specific space, I'm asking you, what is the spatial distribution of these black dots? Are they clustering together? Are they spreading out? Or in other words, are they randomly distributed within this space? Or there is something in the background that controls the spatial distribution of these dots? Okay, so when you're looking at this small space here, you can easily tell that, okay, these dots, they are not clustering together. There is no obvious clusters within this space. Instead of that, you would say, I would say, I think most people would say that, okay, these dots, they are randomly distributed within the space. I cannot say anything that is controlling or trying to manipulate the spatial distribution of these dots, okay? So for this specific small space, you will say that, okay, my conclusion is that all these black dots, they are randomly distributed within the space. That's your conclusion at this scale, okay? That's conclusion one. But if I zoom out, and I'm telling you that this blue small space is just a part of a larger space like this. Now I'm asking you again, what's the spatial distribution of all those black dots within this small blue space? This time you can tell, again, most people will tell that, okay, these black dots, they're definitely not randomly distributed within this huge space. If we're looking at this white huge space, this blue part is just a small part of it. And if we're considering all these black dots within this huge white space, you can consider this blue space is a small part of this white space, okay? So all dots, they are not randomly distributed within this white space because a lot of them, they're clustered within this blue space. So conclusion two, I'm asking you again, you need to get a conclusion two, draw a conclusion two here. What is the spatial distribution of all black dots within this white space? It's not randomly distributed anymore, okay? Even I'm asking this, I'm narrowing down. Okay, I'm narrowing down. What's the spatial distribution of all those black dots within this blue small space? Again, I asked the same question, right? So this time they are clustered. They are clustered. They are not randomly distributed. Like when you saw this first small blue space, because the scale changed, your conclusion also changed from conclusion 1, randomly distributed, to conclusion 2, not randomly distributed. They are clustered within the space. Okay, so you can say when the scale changes, your conclusion could also change. So this actually, again, emphasizes importance of scale in remote sensing and actually in GIS and in geography. That's the first part of MAUP. The second part of MAUP is about dividing a specific area into small regions. And when you are using different methods to divide the space, you could have different conclusions. For example, we have a rectangle space here, right? And within it, there are yellow dots. Okay, they're randomly distributed within the space. You can tell that. There is no obvious clustering, but when you are using 3 methods to divide the whole rectangle space into small regions, you can say that within each region, okay, say let's calculate the density of dots within each region. Because you use the different methods to divide the space, okay, the number of regions changes. Okay, so here we have 1, 2, 3, 3 by 1, 2, 3, 4, 12 small regions here. In this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Different numbers of small regions, and they have different boundaries. If you calculate the density of dots in each region, obviously you will have totally different results and you will draw different conclusions. That's the reason why um, uh, dividing a state or dividing a county into small enumeration units is always controversial. Okay, people will always argue we should do this instead of do that because it's about political issues. It's about people's rights. And you know that now you know that this is actually a part of MAUP problem. When you use different methods to divide a space into small regions, you need to be very careful. Okay, you need to give a solid reason why you are using the current method instead of other methods to defend what you are doing here right now, right? Dividing the space. So that's the second part of MAUP. So MAUP is about scale, is about the method you use to divide a larger space into small regions or small spaces. And this is crucial to remote sensing. Why? For example, here, we have 9 pixels here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 pixels here. Let's just assume these 9 pixels, they are from a classified image array, which means that each pixel here has a specific value, right? And that value is represented by different grayscales here. And each grayscale, or in other words, each value here is connected to a specific class, right? Let's just focus on the central pixel here. It's dark. Let's just assume this pixel is urban area. So class 1, class 2, class whatever, but it's urban area. Let's just assume that. So at this scale, each pixel is simply represented by a grayscale. And at this scale, we say, okay, the central pixel, urban, down. But if we zoom in, this is maybe the fact of that central pixel. If we zoom in, we can see that within this pixel, we have shadows. we have building roofs, we have parking lots, we have cars, we have grass, we have tree canopies. Obviously, the conclusion should be changed when you zoom in to this specific pixel. Before zooming in, this pixel is simply urban. That's it. We cannot get even more information without subpixel classification. But if you zoom in, your conclusion should change. You cannot simply say, okay, this is urban. Well, in general, you can say this is an urban area, but you actually can retrieve more information after zooming in, because this pixel is much more complex than simply calling it urban. Right? So this actually introduces another issue of urban remote sensing. It's called heterogeneity of urban areas. In other words, within each pixel, say, let's just assume this pixel is 30 meter by 30 meter. Within each pixel, within each urban pixel, it's just too complex. Each pixel is not homogeneous, it's heterogeneous, which means there are a lot of things inside. There are a lot of land cover types inside. So urban landscape is composed of a diverse assemblage of materials, vegetation, concrete, asphalt, metal, plastic, soil, water, etc., etc., most of which are man-made. And urban objects are usually small in size when we compare to wildlands, to agricultural lands, right? For example, forest. When we're talking about forest, it usually means a lot of trees, right? And agricultural lands, large areas covered by crops, water bodies like a lake, like a very long river, like ocean. But this is not the truth for urban areas. Okay, so remotely sensed data employed in urban studies is usually with medium spatial resolution, right? There is no very strict definition for medium spatial resolution, but usually we consider 30 meter as a very typical example for so-called medium spatial resolution, okay? Within each pixel, one pixel usually contains several land cover types. Let's just use this example again. So how to address it? I mean, you can say, okay, this pixel is urban if your application does not require more. I mean, if the accuracy requirement is not that high, you can simply say, okay, urban, that's good enough. Then okay. But sometimes we want to say more. We want to get more, we want more detailed information. So this time, we need something called subpixel classification, because obviously this 30 meter by 30 meter pixel is not that simple. There are multiple land covers within. So let's jump to the third part of this lecture, how to do classification in urbanized areas or in urban areas. Okay, like I mentioned, there are so many land cover types in urban areas. So we want to simplify that. We want to streamline that. Is there a way to simplify the complex urban landscape? Okay. Because there are just too many land covers, and sometimes it's just simply not necessary. Okay, we're digging in each single pixel, and within each pixel, we don't want to make it too complex. So if yes, how to reasonably simplify it? What's left in the simplified model? So here is a widely used, very popular model by people who are interested in urban studies with remote sensing technology. It's called VAS model. Okay. It was proposed by Reid in 1994. VAS means vegetation, impervious surface, and soil, which means that we consider that there are only 3 land cover types in urbanized areas, which are vegetation, impervious surface, and soil. Vegetation includes trees, could be tall trees with huge canopies, or small trees or shorter trees, right? And grass. Basically, that's vegetation. Impervious surface is the most complex part. It includes concrete, asphalt, metal, plastic, glass, and all materials that water cannot penetrate. That's why it's called impervious surface. Impervious to who? Water. Okay, water cannot penetrate. And the third land cover here is soil. Soil is, again, relatively simple, just like vegetation. But the tricky part about soil is that you need to know it is wet soil or dry soil. They have totally different reflectance spectra. Okay, that's not a that's another story. I'm not going to uh, go deep. Okay, but now you should know we have a triangle here. We have a triangle with three corners. The top one is impervious surface. That's one um, extreme. Another one is called soil. The third one is called vegetation. So we have three sides for this triangle, right? If it is pure vegetation or pure impervious surface or pure soil, then it is easy. But in the real world, it's not possible. It's always a land cover type between two of them. For example, let's say medium density residential area is somewhere between impervious surface and vegetation. Why? Because in residential area, we have roofs, right? We have pavement, we have parking lots. They are impervious surface, but we also have trees, grass, right? So it's not pure vegetation, neither impervious surface. So medium density residential is somewhere between vegetation and impervious surface, right? If it is high density residential, then it's closer to impervious surface. High density means high density of buildings, houses or apartment buildings. So there are more buildings than vegetation, but still you cannot imagine a residential area without any vegetation, right? So there is still vegetation, but it's closer to CBD, closer, in terms of land cover, closer to impervious surface. So we can do this, the similar thing for row crops, rangeland, forest. I mean, they are not common in urbanized area, but since we have vegetation and soil, let's just assign some land cover types along this side between vegetation and soil, right? And for urban areas, it's more likely there is a combination of soil and impervious surface. Heavy industrial area, right? Industrial area means that there are factories, there are roads, there are pavements, and there is barely vegetation. There could be construction sites within industrial areas, and soil can widely be found in construction sites. So this is the model of VIS, this triangle here, okay? So next, with that triangle VIS model, we want to find a subpixel classification method to address land covers within a pixel. And the method widely used today is called linear spectral mixture analysis. It's a complex name. Usually we call it LSMA. What does it mean? Let me tell you. So here, let's just consider this square is a pixel, This blue square is a pixel, okay? And within this pixel, there are impervious surface, soil, and vegetation, VIS. Let's just assume three of them, they are all within this pixel. And we call this pixel a mixed pixel because there are more than one land cover type within this pixel. If this pixel is completely occupied by impervious surface or soil or vegetation, we call it a pure pixel. And for a pure pixel, it's not necessary to to unmix it because there is only one land cover type. The tricky part is that in urban areas, because of the heterogeneity of urbanized areas, most pixels in urban areas, they are mixed pixels. Not necessarily having all three land cover types, but it's not likely to have only one land cover types. I hope that's clear enough, okay? So now we have three land covers in this pixel. We want to unmix it. What do you mean unmix it? It means that in the end, I want to know the abundance of all three land cover types. What is abundance? You can consider abundance as an area occupied by a specific land cover type. Let's just say impervious surface here. According to this illustration, it occupies 50% of the pixel, right? Then we say the abundance of impervious surface within this pixel is 0.5 or 50%. It doesn't matter. It's the same idea, right? So eventually, we want to know that for each pixel, I want to know the abundance for impervious surface, abundance for soil, and abundance for vegetation. It could be 0, right? There could be no soil, then 0. But that's the idea. That's what we want. So how to do that? Now we introduce another term here. It's called end member. Okay, it's another word for land cover type when we're using LSMA. And usually when we're following, there could be more end members, but if we're following VIS model, we have three end members, V, I, and S. Okay, we want to know the abundance of end members after the classification. So how to do that? How to do that? For example, now we have done that. I'll tell you how to do that later. But now let's just assume we have results, okay? So for vegetation, abundance is 40% impervious surface, 50%, soil 10%, okay? Eventually, this result, this abundance is what we want from LSMA. So how to carry out LSMA? This is how we do it. It's very simple. Okay, in LSMA, we assume that the reflectance of the single pixel is the linear combination of reflectance from all land cover types within this pixel or all end members within this pixel. So if this was the result of the unmixing, it means that 40% of the total reflectance of this pixel is from vegetation. 50% of this pixel's final total reflectance is from impervious surface. And 10% of the final reflectance of this pixel is from soil. So you add them up linearly, you have what? You have this pixel. You have this pixel's reflectance. Okay, now based on that linear idea, we have this formula 1. So on the left side, we have RB. RB is the reflectance of band B for a pixel. So this is the total reflectance I mentioned before for that single pixel. And N is the number of end members selected from the image. Okay, here is capped N. Usually it's 3, right? Because usually we have 3 end members: vegetation, impervious surface, and soil. Okay, Fi is the fraction of end member I. Fraction is another word for abundance. You can consider Fi is the abundance of end member I. So Fi is something we want. For vegetation, Fi is 40%. For impervious surface, Fi is 50%. For soil, is 10%. So Fi is something here we want to solve. We want to get from this formula. And Rib is the reflectance of end member I at band B. So this is Rib. You use Rib to multiply Fi. And you calculate the sum for all what? for all n members from I equals 1 to I equals n. What does it mean? It means that you use the typical reflectance of an n member to multiply its abundance or its fraction within this pixel to get its contribution to the total reflectance of that pixel. And you do this 3 times, it means that you have calculated the contributions of all 3 land cover types or all 3 n members, and you add them up, you have the total reflectance of that pixel. Okay, so this is the idea of linear combination of reflectance from all 3 land cover types or all 3 n members. Okay, so this is essence. This term here is the essence of LSMA. And eventually there could be error. So EB is the model residual or error at band B. So you would ask, now we have 3 Fi to solve because we have 3 n members, but you only have 1 equation here. How to solve that? You have how to do that? Good question. Then you use 3 equations. This equation is from band B. How about you get another equation from band A, another equation from band 3, and you do the same thing for 3 bands. Then you have 3 equations and 3 Fi's. Then, according to mathematics, you can solve this equation group or equation set. 3 Fi's to solve. We have 3 equations. It's linear, right? So that's it. So you can say that with a little bit algebra knowledge, this linear function is very easy to comprehend. Maybe not very easy. It's not hard to say that to comprehend. And here, equation 2 is what? Equation 2 is just a constraint for Fi. So the sum of Fi should be equal to 1, right? Because totally it should be 100%, right? Because you just assume that in each pixel there are 3 land cover types, 3 n members. Eventually, when you solve these 3 equations, you should have 3 Fi values, right? If you add them up, they should be 100%, just like this: 40% from vegetation, 50% from impervious surface, 10% from soil. So totally is 100%. Right, because the whole pixel should be unmixed. If it is not 100%, where is the rest? It's not possible, right? So you add them up, the sum of Fi should be 1, and Fi should be equal or larger than 0 because a percentage, right? If you get a value, a negative value, obviously there was something wrong with your a solution of this equation set. Okay, so this is LSMA. And it's the most widely used method for unmixing mixed pixels in urban areas. But this is linear. How about unlinear? Okay. If you say there is, I assume that the total reflectance of a pixel is a nonlinear combination of the 3 land cover types. Then your equation here should also be nonlinear, but it will be more complex. That's for sure. But currently, usually LSMA is good enough. We usually consider that the reflectance of a mixed pixel is a linear combination of all n members, linear combination of reflectance of all n members within this mixed pixel. That's good enough. Okay. So the fourth part of this lecture is about urban heat island. It's one of a lot of topics. Okay, when people are trying to use remote sensing to address urban areas. Okay, urban heat island is one of the topics. So what is the concept here? So urban heat island is called UHI. it refers to the phenomenon that temperatures, okay, could be air temperature, could be surface temperature. Temperatures in urban areas are higher than surrounding rural areas due to the change of atmospheric and surface conditions caused by urbanization. So this is an illustration of urban heat island. So here, this is downtown. It is surrounded by commercial areas, urban residential, maybe some parks, and then we go to suburban residential. And if you drive away, you continue to drive away from downtown, then you eventually go to rural areas, right? And this is a profile or cross section of a typical city around the world, right? And when we're talking about the temperature, this red or say pink area is what you say. So the vertical axis is for temperature, okay, in Fahrenheit in summer. So you can say in downtown area, in the downtown area, usually the temperature is the highest. When you're driving away from the downtown area, you're driving away from the downtown area to the right. Well, this arrow is just too wild. No. You're driving away from downtown area to the rural. You see that the temperature is dropping, right? So obviously there is something wrong with urbanization. It brings more thermal energy, right? So this is urban heat island. And why? The most important factor here is impervious surface. Okay, they're pretty good at what? Absorbing heat from the sun. And they're pretty good at storing or keeping those energies inside instead of discharging them. Okay, less cooling from evaporation and plant transportation. Why less cooling from evaporation? Because water cannot penetrate them. Water will evaporize above them, or water, because water cannot penetrate, there is less ground storage of rainfall. Water will be discharged into sewers, and sewers would just discharge water to surrounding rural areas. So water cannot stay in urban areas. In general, you can say that. Okay, so there is less evaporation within cities. And on the other hand, these materials, impervious materials, asphalt, concrete, metal, glass, they're pretty good at absorbing solar energy, and they're pretty good at keeping them. So that's why urban areas, they are hotter than surrounding rural areas, right? Surface absorbs less heat in rural areas, and greater ground storage of rainfall. And when water penetrates soil, and within soil, they still evaporate, and they will just bring a lot of heat off the ground during the process of evaporation. Okay, greater cooling from evaporation and plant transpiration, and the abundance of vegetation is another factor leading to urban heat island, right? Because there is less vegetation within cities, and the vegetation can cool surrounding areas by what? By evaporation of water, also by something called plant transpiration is actually another form of evaporation. So this is why we have urban heat island. If you divide this figure into two parts, on the left side we have urban, on the right side we have rural area. And you can say the balance of thermal energy is different. Okay, this is why urban heat island is important, because high temperature is not friendly to people who live in cities. And as a result, we use air conditioning systems. We use different methods to cool ourselves, especially in summer. And those solutions, for example, air conditioning systems, they are making the air even hotter. You're cooling yourself and sacrifice the surrounding environment of yourself outside of your house, outside of your office and apartment. And also there is also pollution, air pollution from air conditioning systems. For example, when you are using AC in your car, you are actually consuming more gasoline to do that, which means more carbon discharge, more pollution to the air. Okay, so urban heat island, you can say it's simply about temperature, but it is affecting, it is impacting a lot of aspects of our life, of our environment, of ecology. Okay, I will stop here for this video, and next video, I'm planning to introduce um, some part of my research for my PhD dissertation, because that dissertation is about remote sensing's application in urban areas. So I can share some of my research to you, and it will not be very complex. I will just ignore the complex part and show you some relatively straightforward part of my research. Okay, thank you.